Okay, perfect. So I'm Calen Henderson. I'm a relatively new staff scientist at NearInfrared, the NASA Exoplanet Science Institute. And you might notice I actually have a cast on my thumb. You saw Scott with a cast on his toe. If anyone asked, those events were entirely unrelated and had nothing to do with arguments with collaborators or anything like that. Plus, as the saying goes, no sprain, no gain. The jokes are not going to get better, so I'm going to warn you ahead of time. So today I'm going to talk about the K2 Campaign 9 satellite parallax observational campaign. And Jen and Scott and Rach gave a series of excellent introductions. So rather than saying it every time this comes up, I'm just going to say that a lot of the information that I'm going to present, especially at the beginning, you'll have already heard from at least one of their talks. So hopefully you either already know it or you're familiar with it. And then going to go a little bit of a different direction, and instead of talking about theory, talk about some actual observations, so some actual observed light curves from this campaign last year. So without any further ado, just a couple of quick background slides on microlensing now that everyone's experts from the morning talks. So a microlensing event occurs when you have the light from a background source star, that's this stationary object in blue here, is amplified by the gravitational potential of an intervening foreground lens system. It's kind of the one-sentence summary. And that's the red star, the lens host star. It does have a planet. You can see when the planet is roughly coincident with one of the images created by the stellar microlensing event, you get a perturbation on the light curve. So there's this deviation in the magnification structure. And Scott and Jen and Rach have already walked through a bunch of examples of how to identify where there are anomalies and how to just qualitatively quickly try to characterize what type of an anomaly they might be. I have a lot of videos, so hopefully this will help make sense. We can actually zoom in a little bit more, so I'm showing another kind of toy model microlensing event. Here you see, due to a single body lens, smooth, symmetric, and timed light curve. And if we really zoom in, here you can see the two images of the source that are created over the course of the event, and you actually saw as they traced out the Einstein radius throughout the course of the event. And as Scott, as people have mentioned, the angular scale of the Einstein radius is about a milliarcsecond, a few hundred microarcseconds. So that's why, in general, we're just measuring, as shown here in the bottom right, in the light curve, just the brightness. The magnification is a function of time. You're not actually spatially resolving the actual two images that are created. As we've also heard, there are kind of three general regimes of exoplanet demographics that microlensing is capable of exploring, whether uniquely or in tandem with some of the other detection techniques. In no particular order, this is cold and bound exoplanets, so planets that are farther away than the sensitivity regimes generally of the transit and the radial velocity method. And then there are free-floating planets, so these would be single lens light curves, but that lack any sort of stellar signature, and then can explore the galactic distribution of exoplanets as well. So just to briefly point you to other talks that are going to go about these more in detail. So there's going to be a series of talks tomorrow morning by Yossi Schwarzwald, Daisuke Suzuki, and Christian Clanton. They're going to go into far more detail about kind of the state of the union of what we know about cold and bound exoplanet demographics from microlensing. I'm going to show quickly, on the left is a histogram of the timescale distribution as reported by the MOA collaboration in a paper led by Takasumi 6 years ago, in which there was potential evidence for a significant population of free-floating or unbound Jupiter-mass planets. And on the right, I'm showing a very hot, very new result from the OGLE collaboration. Again, it's a timescale distribution. This is figure 2 from their paper. This is a detection efficiency corrected one, where they don't necessarily find the evidence for that population of Jupiter-mass free-floating planets. But as the timescales get to very, very small values, about 1/10 of a day, there's potential evidence for Earth mass, roughly, free-floating planets. But again, I'll direct you. So Taka is going to give a good overview talk about this tomorrow morning as well. So ask all of those people all of the difficult questions. And then you've seen a version of this plot already, I think, in Rach's talk. So these are data points pulled from the NASA Exoplanet Archive. I'm showing planet mass on the y-axis and planetary system distance, so distance from Earth on the x-axis. And I've point and color-coded the different detections according to detection technique. Microlensing are the purple pentagons. So let's see, these data, I think it's about 6 months old. So there are 844 planets on this plot. And overall, microlensing is about 4% of the known exoplanets. here. But you can see if you start making cuts for planetary system distance, microlensing detections start accounting for a larger and larger fraction of the known planets. So once you go a planetary system distance, dp, greater than 1 kiloparsec, the fraction of detections that are from microlensing rise to about 40%. And then if you're talking about systems that are 2 kiloparsecs away or farther, it goes to about 70%. And this is one of the strengths of microlensing, as we've seen earlier, is being able to probe this across a wide range of heliocentric distances. So for microlensing, what are the standard observables? We've talked about a bunch of different fit parameters you can get from a single lens model or from a two-body lens model. And in each case, there are kind of two that are the most, I would say, just closely associated with the physical parameters of the lens system that you ultimately want to derive. In the case of a single object lens, so just an isolated star or a free-floating planet, it's the timescale. It's the most salient observable. And in the timescale is encoded distance to the lens, distance to the source, mass of the lens, and the relative transverse velocity in the plane of the sky. And then the finite source size, this parameter rho. And, we've heard a little bit about it. We're going to go into more detail, especially Wednesday when you do the fits. And then once you add a second body, so if we're talking about a bound exoplanet, orbiting one star, you also have the mass ratio, planet divided by the star, and their instantaneous angular projected normalized separation, S, which ultimately we wanted to turn into a projected semi-major axis in physical units. As well as the kind of two main parameters, and these are the ones that by no accident I was just showing on the previous demographic plot, the lens mass and the lens distance. And so one of the questions we want to ask and answer is, how do we go from these observables to these physical parameters? Jen showed this equation earlier. I believe this is the only equation I'm going to show as well. So hopefully you already have it tattooed on the inside of your eyelids or something. So basically, if you want to get the lens mass, one way to understand it is if you measure the Einstein radius, theta e, and kappa is just a constant. If you measure the microlens parallax, this pi e, then you have solved for the lens mass. And assuming a source distance, you can get a lens distance. And this is how you get these parameters. So Jen gave a very, very excellent kind of theoretical understanding of the different types of parallax, how do they manifest themselves. And what I'm going to do is I'm going to go kind of one step in a tangential direction and show a series of animations that I created. They're born out of conversations with Yossi Schwarzwald, one of my colleagues here in Pasadena. Right before Campaign 9, we were trying to understand the sensitivity of the spacecraft in terms of what is its projected separation from Earth during the campaign, and how does this relate to this quantity RE tilde, so the projection of the Einstein radius in physical units onto the observer plane. And ultimately, we created some of these animations, and I actually learned a little bit from them, so hopefully you all will also learn something, or at least promote a little bit more intuition about what parallax looks like and what it means. So to start the first one, what we're doing is we're looking at the solar system top down. Yellow is the sun, blue is Earth, orange is Kepler. And in the top left, I'm just incrementing the dates of K2's Campaign 9. And in the top right, I'm showing what the projected separation from the center of the survey area, so you're kind of looking, if you're looking at the solar system, at the solar system from the Galactic Bulge, what is the separation on the plane of the sky from your perspective of these two observatories? This is one of the channels that Jen discussed. And so you could see how that evolved. It was from roughly 0.07 AU, the beginning of the 0.11 at the beginning, dipped down to 0.07 AU, and then went to its maximal value at the end of the campaign of 0.82 AU. I have also included Spitzer. So you see in orange, the Spitzer orbital trajectory as well. So both Kepler and Spitzer are in an Earth-trailing solar orbit. In general, the projected separation between Spitzer and the Earth is a little bit larger than that of Kepler's, but it's of order the same magnitude, this sweet spot that Jen was kind of talking about earlier. So now, the left panel here is the same thing as the previous panel. And in the right panel, all we've done is we've tilted it. And so we're looking at it from the center of the K2 Campaign 9 survey area. Here, because I've gotten this question before, the center of the observations is not in here. It's not inside Earth's orbital circle. This is just giving the direction. In these units, the bulge would be x equals 0, y equals minus 1.7 billion. And on the right panel, we've just basically rotated it 90 degrees. And so this, here you can get maybe more visually apparent idea of what this projected separation is. It's exactly this distance as looking from the center of the superstamp. Now what we're doing, again, we're looking from the perspective of a source, and we're looking through an Einstein ring for a toy model lens system. So a lens that's at a distance from the Earth of 4 kiloparsecs, isolated star with a mass of half a solar mass. And now we're co-moving with that frame of reference. The galactic plane is z equals 0, z prime, and we're watching as the solar system, with the same bodies marked as before, kind of goes through this Einstein ring. And so if we put it all together, now what's happening in the bottom right panel, all the other three are the same as what we've seen before. You're going to see the light curves from those 3 observatories for this toy model event over the course of the campaign. And so you can see Kepler in orange, it has the smallest separation, and as people have mentioned, that's going to give you the largest magnification. Then you can see the Earth-based or ground-based light curve here in blue. And then since I'm more highlighting K2 than Spitzer, you just get a trailing bit from Spitzer here, just for this example toy model event. You can very clearly see that there's this characteristic shift in the magnitude of the peak magnification. So it's about a factor of 2. So the impact parameter, this U0, differs by about a factor of 2 from Earth and Kepler. And there's even, it's harder to see on this scale, but you have this 1.5 day separation of the time of this peak magnification as well. And so these are the 2 observables that you leverage in order to measure this microlens parallax, this separation in time and the separation in peak magnification. So Josie and I went on to write just a quick paper talking about the sensitivity of K2 Campaign 9 specifically to free-floating planets. And again, I want everybody to be thinking about the relationship of the Einstein radius on different planes. So what I'm showing in the left panel here, this is the projected separation. So again, the plane of the sky, the separation you would see from the bulge between Earth and a given observatory. And so at the very top, we have New Horizons. That's basically an order of magnitude higher than what you would get for Spitzer in red. Kepler throughout the Campaign 9 in blue. That's what this is. So it had dipped down to its minimum, gone back up to its maximum. And then this is Campaign 11, which you'd get for Kepler. And I'll talk very briefly about this at the end of the talk. Then here's W first. It's at L2, and the full orbit is the kind of wider shaded purple region, and then the actual observing seasons during which it will likely conduct the microlensing survey are the darker purple regions. And then I've shown just the maximal separation of SWIFT from the Earth. So you can see these different satellites span several orders of magnitude. And for the reasons Jen was mentioning, there's different caveats and strengths to each of these. And I've shown on the bottom just, again, as a function of generic year, for how long is the bulge visible for a given day. And on the right now, I'm showing, as a function of lens distance, what is the projection of the physical Einstein radius onto the observer plane for lenses of different masses. And here I'm just talking about free-floating planets, and so the masses are color-coded up at the top, up until the brown dwarf limit in black. And I've overlaid on that what the minimum and maximum projected separation of the Kepler spacecraft from Earth is throughout the campaign. And so here you can see kind of a sense of the functional form of how this RE tilde changes as a function of lens parameters. And again, I'll refer people as well. You don't have to memorize this chart or anything along those lines. But Jen and I have also put this kind of information in tabular form in this conceptual themes document to kind of guide people's intuition on the website. And to really, really hit home about why Kepler and, by extensions, Spitzer and W first as well are in the sweet spot. What we're doing here is, again, throughout the dates of K2's Campaign 9, we're looking at the top row is that for the same toy model lens event, so half solar mass star at 4 kiloparsecs from the Earth. Oops. Let me just pop it to the end. Pause. what is the light curve, the resultant light curves from both observatories. So left is New Horizons in orange and Earth in blue. Middle is Kepler in orange, Earth in blue. Right is Swift in orange and Earth in blue. And what are the resultant light curves for each of these configurations? And this will help highlight why this sweet spot is so important. The bottom panels are the actual magnification, the light curves in magnification space. So on the left, you have New Horizons in blue. New Horizons in orange, and you can see the blue light curve that Earth sees. So Earth is going to be the same every time, just the scale of the y-axis and the light curve plots is changing. Earth sees a nice single-lens microlensing event, moderate-ish magnification, and New Horizons, because its projected separation is sufficiently large compared to the physical projection of the Einstein radius, it's actually not seeing hugely significant magnification. And then I'm showing the fractional difference between the two here. So Earth light curve will always be at 0. Let's jump over to Swift next. Its projected separation is so small that actually the light curves are going to look pretty identical for this toy model event. The scale here, it's probably hard to read, which is indicative of the issue. It's 10 to the minus 5. And a lot of this kind of sharp features here is just because I'm sampling. Swift's orbit is faster than 1 day, and I'm just sampling it in 1-day increments. So there's kind of a strange sampling error there. Kepler and Spitzer and WFIRST in the middle is where it's just right, the projected separation for the spacecraft. And so you see a microlensing event from both locations, but they're sufficiently different where you can leverage this time of peak magnification and the magnitude in order to measure the parallax. So for those of you, I kind of already gave away my joke a little bit, but for those of you, who have been thinking a lot about maybe habitability and the Goldilocks zone in terms of transit and RV surveys, I guess you could call the orbit of K2 in the context of microlensing in the Goldilocks zone, but specifically that means when considering the physical projection of the Einstein radius onto the observer plane for a roughly typical lens discovered via microlensing survey toward the sun and Milky Way with the source in the Galactic Bulge. Not quite as catchy, but it really is in that sweet spot. So what are the parameters of the campaign? The K2 project office worked very, very hard to give us a significant fraction of their pixel real estate to assign to the survey last year. And it resulted in a total area, all said and told, of about 3.7 square degrees. This was long cadence data, so every 30 minutes. And the start was going to be 7th of April last year and end early July with a campaign duration of about 85 days. Now, as I know many of us in the room are familiar in various respects, right before the microlensing campaign was supposed to start, literally 1 day beforehand, K2 went into emergency mode. And everyone was very worried about the future of the spacecraft, and especially the microlensing survey. And essentially what the spacecraft was saying was just, oh, I'm sorry, K2 science team, I can't let you do that. And what is that? In order to facilitate kind of the maximal science from the campaign, they had to point the spacecraft in the positive velocity vector direction so that you could be simultaneously observing the same area on the sky from the ground and from space with K2. And so right before they tried to do that maneuver, the spacecraft said basically no. However, what I think everybody on the microlensing science team was worried had happened is that we tried to turn the spacecraft around and we'd killed it. And if that had been the answer, microlensers would never have probably gotten another space mission before, or a space mission again. Thankfully, the people, especially the engineers in the project office, worked very, very hard. They fixed it. We lost about 2 weeks of time. So the campaign didn't end up starting until 22nd of April, and then went just a day later than anticipated for pointing restriction reasons. And so it was about 71.4 days. What it meant for our expected number of events, which scaled roughly linearly with our campaign time, is that we took that same hit, about 15%, on our expected number of events. So there were 109 events that were observed in the survey superstamp. So I'm showing a zoom out here, and then a zoom in, where these contiguous patches outlined in red are this 3.7 square degree survey area. And then, in addition to just doing a blind survey of the same area from the ground in space, the K2 project office also allowed us to add specific postage stamps for known microlensing events from both the OGLE and MOA ground-based surveys. So events that we already knew were ongoing and that we could add later to the target list. And so for the first half of the campaign, C9A, we added 34 events. For C9B, we added 61 events. And between the two of those, there were 70 unique events. So about 200 events observed. Oh gosh, is that time? Oh, 5 minutes, thank goodness. So there's a bunch of people involved in making this happen. I'm listing just some of the primary ones here. I'm going to highlight in white. These are people who are specifically here, all of whom are going to give talks. So if you have any questions, feel free to come and talk to us. I've talked a lot about the space-based endeavors, but I haven't really talked about the ground-based resources. So I'm just going to quickly show a couple of map panels that are color-coded, showing different observatories that contributed ground-based data and what their generalized science goal is. So in blue, this includes OGLE, LCO, KMT, MOA. These are at WISE in Israel facilities that were doing an automated survey of the superstamp region. Then there were other telescopes that were doing targeted high-cadence follow-up of specific events, either high-priority free-floating planet candidates or other objects of interest. Then there were some instruments that were doing wide-field, deep, multi-band monitoring. I'm not going to talk too much about this in detail, but that's one way that you can help measure theta E. And then there are a lot of facilities as well making near-infrared source flux measurements. I'm not going to talk too much about that either, but I'll point to JP's talk tomorrow, and he's going to talk a lot about why making near-infrared measurements is useful. Here's an image of the Galactic Bulge just a few degrees away from the center of this survey superstamp, and this is taken with HST. In fact, the most difficult problem for this campaign, and actually largely the reason that not a lot of results have yet come out, even though the campaign finished 13 months ago, is that Kepler's pixels are big, and if you're pointing toward the bulge, the blending is very high, and the stellar crowding can make it very difficult to model your events. So just for scale, this is 1 Kepler pixel, and so you can see you're subsuming the light from a lot of blend stars, not just the one you're interested in. And in fact, this is a plot that Radek Pileski of the OGLE collaboration made. So this is showing the number of stars brighter than a limiting magnitude using the OGLE 3 catalog. And you can see, so on the left, it's per area per square degree. On the right, it's per Kepler pixel. Just per pixel, getting down to the limiting magnitude of the OGLE survey, there's 3 stars brighter than I of 20 per pixel. What makes this even more difficult and potentially intractable is that the PRF for Kepler is often many, many pixels. It's a channel-dependent number, but it's 3 to 7. And so trying to understand the blend in this crowding regime is very difficult. And it's about 10 times more dense than previously the most dense observed areas for K2. And I'm going to point to Scott Gaudi for talking about really from a fitting perspective. He's giving a talk on Wednesday morning for why this is difficult. So I'm going to skip through and then just focus on one of the ways in which people have tried to make this problem tractable is to use an algorithm called causal pixel modeling. And what this involves is if you have a pixel of interest that contains your star, where you think your microlensing event is, what you can do, actually I will go back one slide. What you can do is look at a reference patch of pixels that is far enough away that there's probably no PRF, what I kind of think of as thermal contact between your reference patch of pixels and the star you're interested in. So any common photometric variations between the two are likely instrumental systematics, not things astrophysically similar. And so if you can model those systematics out, you can actually get a handle on what the morphology of your light curve is. So I'm highlighting here a light curve that was produced by Clement Ronc, a postdoc with Dave Bennett, who's going to give a talk right after me at NASA Goddard. And this is for a binary lens event. And they were implementing this. That's what this stands for, causal pixel model plus light curve modeling in order to produce this light curve. Scott referred to these double horned features as double horns. I can't help but see the eye of Sauron every single time I look at it. So if you're wondering why people think microlensing is the dark side, well, this is another event. I've given the phone name very quickly up at the top. This is using a different method. This is by Wei Zhu, who just graduated from Ohio State, where he's using high-precision astrometry plus light curve modeling plus a color-color constraint in order to model the light curves. So this is ground-based KMT, MOA, and OGLE. And here's what he finds, that you can see the shift with the K2 data. There's a third effort that I'm not really going to talk too much about. I'll have you ask Matthew Penny This is another use of the multiband monitoring that I was mentioning earlier. And then I'm quickly just going to highlight that as I mentioned in those light curve animations, there's a little bit of overlap between the Spitzer campaign of 2016, the microlensing survey campaign, and K2 campaign 9. And so there are some events in common there that's interesting. Campaign 11 observes some microlensing events as well. And I'll end by, as any good talk, pointing you to another talk by me tomorrow, in which I'm going to talk about some community resources and data and tools that are available to kind of dig into this data set and other future microlensing data sets. So thanks, and I'll take questions. Yeah, so the, oh yeah, I can repair it. So the question was, how did we determine, or how was determined the cadence of the observations? So for Kepler, since or K2, since it's using the Kepler, all of the Kepler equipment, it's the same spacecraft. If we had done short cadence, which we didn't really need to resolve a lot of the features, but that would have meant that we would have been able to download a correspondingly smaller pixel area. So we went with long cadence was kind of the natural choice. One of the other difficulties of doing this kind of modeling, though, a 30-minute integration, can smooth over even just during one exposure. But for caustic crossings that are very sharp, or small source sizes, or finite source effects, you might have to take into account the magnification change during an integration. And then really, especially for the surveys, Ogle, MOA, KMT, they already had set survey strategies that had cadences of maybe 10 or 15 minutes, depending on the part of the survey superstamp they were observing. And so they just continued with their standard operations.